Good afternoon, committee members. Our team number is 2563335. Thank you all for taking the time to be here today to participate in the defense of our paper titled SEIR Modeling the COVID-19 Pandemic in Hong Kong. So without further ado, we shall proceed to these 5 key sections today. Our studies aims to explore more about the onset, peak, and resolution of the major COVID-19 epidemic waves in Hong Kong using the SEIR complemental model. Our critical analysis of the time-varying reproduction number is also conducted to assess the direct impacts of various public health policies and interventions throughout each wave. We adopted the SEIR model for checking how the pandemic spreads by dividing people into 4 groups. Susceptible, which means healthy individuals. Exposed, which means individuals who are infected but not showing symptoms. Infectious, which means sick and spreading individuals. And recovered ones with immunity. To collect data for our research, we made reference to official government publication, daily confirmed case counts, quarantine center occupancy statistics, and peer-reviewed studies on Wuhan for understanding the early dynamics of the pandemic. We also integrated additional sources, e.g., reports from the Center for Health Protection, CHP Hong Kong, and studies on Hong Kong's COVID-19 responses to enrich our perspective and corroborate our findings. By integrating these diverse and credible data streams, we ensure a holistic and well-supported understanding of the situation. The flow or transition between these compartments is governed by the following system of differential equations. The SEIR model uses differential equations to check population changes through 4 states: susceptible, exposed, infectious, and recovered. It calculates the flow rates using parameters like the transmission rate beta and recovery rate gamma, enabling the predictions of epidemic dynamics. For this model, we need to estimate some parameters in order to find the numbers of exposed, infectious, and recovered. We estimate the transmission rate beta for each outbreak wave using nonlinear least square optimization. This fits the model to real data by minimizing the prediction errors as well as capturing changes from interventions and viral evolution. The incubation rate and recovery rates are fixed. They are calculated as the inverse of the mean incubation and infectious periods from previous research. We may use the parameters mentioned above to estimate the basic reproduction number R0. It is given by beta divides gamma. R0 is the average number of people one infected person can spread the disease to. If R0 is greater than 1, the outbreak grows. If R0 is less than 1, it declines. High R0 means a more infectious disease. This model has important assumptions and limitations. It assumes people mix equally and that key rates are constant during an outbreak. It does not account for age differences, asymptomatic cases, or waning immunity. Based on government data, we estimated sigma, beta, and gamma. From this, we divide the values for exposed, infectious, and recovered populations over time. The resulting graphs and data are presented below. We applied the SEIR model to the first wave, during which aggressive public health measures were enforced. This measure successfully contained the outbreak. Despite an estimated reproduction number of 0.2, the resulting epidemic curve in figure 4.1 demonstrates this effective suppression. We compare the simulated total number of infected with the data from CHP. The difference is around 70 individuals. Wave 2 was driven by imported cases. Border controls were pivotal, effectively limiting community transmission. Our analysis estimated the basic reproduction number at 1.8. As shown in figure 4.2, the SEIR model indicates the epidemic was successfully contained. The difference between the simulated number and the actual number is under 10, which is a quite satisfactory simulation. As for the rate 3 saw significant transmission clusters in restaurants, workplaces, and care homes. The estimated transmission rate and reproduction number were the highest among the initial rates, driving the first major local outbreak. The SEIR curve in figure 4.3 illustrates this substantial community spread. Starting from rate 3, the simulated number of infected is significantly higher than the actual number from CHP. But similar to other research conducted by local university, this may be due to more asymptomatic patients in the community from rate 3 onwards. Then, this fourth wave was characterized as a prolonged surge lasting nearly 6 months, influenced by repeated tightening of social distancing policies. For this wave, our estimated parameters yielded a basic reproduction number of 1.9. The estimated transmission rate was 0.27, while the recovery rate was fixed at 0.14 per day. Then lastly, the fifth wave was driven by the Omicron variant, causing an unprecedented surge. Case counts exceeded all previous waves combined, and the elimination strategy collapsed during this period. The SEIR model indicated a much higher transmission rate, consistent with Omicron's increased infectiousness. For wave 5, the estimated transmission rate was 0.55. This higher rate resulted in a derived basic reproduction number of 3.9, which is nearly double the figure estimated for wave 4. So to have a short conclusion, the initial waves show successful containment through border controls. Later waves indicated challenging local spread. Finally, the Omicron wave saw a dramatic surge, overwhelming prior elimination strategies. These progressions reflect the city's pandemic challenges. Early policy successfully suppressed initial waves. However, wave 5 reveals the fragility of that strategy and the critical needs for adaptable, sustainable policies. The severity of Omicron was amplified by elderly vaccination rates, underscoring that widespread vaccination is essential for future preparedness. In summary, future research should develop more detailed models. This includes extending the SEIR framework to account for vaccination and waning immunity, as well as incorporating realistic factors like age groups and social context patterns. That's all of our presentation. Thank you.